Hey everyone! So in this video I'd like to talk about some common formulas. So we'll cover some examples of formulas that appear frequently both inside and outside of the classroom. I should say that we haven't used this word formulas before. Really, formulas just mean an equation that we can use to compute some values. So I don't really want to focus too much on that, but maybe let's just go into some different examples. I'd also like to say that I wouldn't recommend memorizing these formulas. I don't think there's such great benefit in doing that. But one thing I would recommend is try and see if you can understand why these different formulas are true as we go through them. And if you're ever confused about these formulas, I would definitely encourage you to use some small examples to remind yourself why these formulas are true or why they are the way they are. But anyways, let's talk about this example here. So here we have the statement that says a vehicle is traveling at a consistent 60 miles per hour. And we're asked how far has this vehicle traveled after 2 hours and after 3 hours. Well here, if we have a vehicle that's traveling 60 miles per hour and we let it travel for 2 hours, well that first hour it's going to travel 60 miles. And then that second hour it's going to travel another 60 miles. And so there will be a total of 120 miles traveled, right? And actually, it might be clearer to see this as two sets of 60, right? 2 times 60. It's really the same as 2 times 60. And so here, 2 times 60 gives us 120, and that's the number of miles this vehicle travels after 2 hours. And then similarly, if we're asked to figure out how far this vehicle's traveled after 3 hours, well, here we would just take 60 for the first hour, then they would travel 60 for the second hour, and then 60 for the third hour. That's 60 plus 60 plus 60, or 180. But really, that's the same as 3 sets of 60, or 3 times 60 is 180. Right, so here, really, in general, the distance traveled by an object moving at a constant rate for a specified time. So this is kind of a long definition, but here, let me really just work through this. For a specified time is, well, it's the distance is equal to rate times time. So I said, in general, the distance traveled by an object moving at a constant rate for a specified time is, well, the rate times time multiplied together. That's what gives us our distance. And so here, let me expand on this idea here, constant rate. So constant just means that it's not changing. Right, so in our above example, we said that this car was traveling at 60 miles per hour, a consistent rate of 60 miles per hour. It's not really moving too far away from 60 miles per hour. So we can really, say that the distance traveled was 60 miles for each of those hours, right? If it's changing, then we can't really make the same conclusion. So here, this formula for the distance really depends on our object traveling at a constant rate, a rate that's not changing. Right, so if we look back at our example above, here, the rate was 60 miles per hour. This was the rate, or the speed. And then here, we were told some different times for which that vehicle traveled. But here we just multiplied that rate with the time together to get the distance. That's really the idea of this formula here. Distance is equal to rate times time. And here if we labeled, distance as the letter D, rate as the letter R, and T as the letter time, we might say that D is equal to R times T. Right, and here remember that multiplication between two variables. Sometimes we'll just leave that operation out and we'll just put the two variables side by side. And because there's no operation between those two variables, that means they're being multiplied. So I have an example here where we can use this idea of distance is equal to rate times time. Here we're asked to write an expression for the distance a plane traveled after t hours if that plane flew at a constant speed of 180 miles per hour. So here what this is saying is that here's our rate, right? So here this constant speed of 180 miles per hour. This is our rate. Maybe I'll use the symbol R. And then here we're already told that we don't have any particular amount of hours traveled. We're just given this letter, this variable amount, t hours. But if we multiply whatever that quantity is, whatever t represents, when we take that number and we multiply it with the rate, we're going to get the distance, right? So here, just to reiterate, distance is equal to rate multiplied with time. This really gives us the distance. This isn't division here, I'm just underlining it to really emphasize. And so here, if we want an expression for the distance this plane has traveled, what we're really going to do is we're going to take 180, our rate, and we're going to multiply it with the time this plane spent traveling. So 180t, this is really an expression for the distance traveled by the plane. And so here, if we're going to, this next question asks, it says, how far will the plane travel in 3 hours, 3.5 hours, and half a day? And so here we can compute that distance by using our expression here, right? So this is an expression that figures out or determines the distance the plane has traveled. We just need to plug in different values for time to see that distance. And so here, if I want to know how far a plane traveled after 3 hours, well, I'm just going to take this value for t and replace it in our expression. So here this is 180 times 3. This gives us 540. And then here, I wouldn't leave our answer like this. This isn't really telling us the meaning of our answer. It just says 540. Well, 540 what? 540 miles. The plane traveled 540 miles after 3 hours. Maybe let me write this in one concluding sentence after I've answered the other two questions as well. So here, if we want to figure out how far the plane has traveled after 3.5 hours, well, we would just plug that in to our expression. Actually, maybe let me use that same color here. So this is times. And so to make this maybe a little bit clearer, I might use 3.5. So mixed numbers that contain, the whole number part and the fraction part together, these are a little bit more challenging to work with, to do mathematics with. And I think either having an improper fraction, where it's just all, numerator and denominator, there's no whole number part, or a decimal, these are two things that are easier to work with mathematically. So here, maybe I'll write this 3.5 as 3.5. And actually also to make this more clear, I'm going to write a little tiny x symbol as multiplication because there's a dot already used for the decimal. And those two dots make things a little bit less clear. And so what's 3.5 times 180? Well, I know 3 times 180 is 540. Right, 180, 360, 540, and then an extra 0.5 times 180, well, that's 90 on top of that, giving us 630. And in the last example, well, we want to figure out how far the plane traveled after half a day. Well, half a day, that's 12 hours. So what we're going to do is we're going to take our rate and multiply it with the time, 12, right? 12 hours. And this is going to give us, this might take a little bit more effort. I know 10 times 180 gives me 1,800. And I still have to add on 2 more sets of 180 on top of that. In other words, I have to add on 360 on top of my 1,800, and that comes out to 2,160. And so let's state our conclusion from all of these results. So here, what we can say is that the plane traveled 540 miles after after 3 hours. It traveled how many miles? 630 miles after 3.5 hours. And then it traveled 2,160 miles after half a day. So one other thing I want to mention is that here, this whole process where we plugged in numbers for our variable, I just want to reiterate that this process here, plugging in numbers for our variable, this is what we called evaluating in the last video. I didn't take too much time to talk about this idea of evaluating, but here what we did was we evaluated our expression at t is equal to 3, at t is equal to 3.5, and at t is equal to 12. So evaluating just means plugging in some number in for the variable and then computing the result. So there are numerous geometric formulas out there, and many of these are used to compute the perimeter and the area for different kinds of shapes. And so here, maybe let's remind ourselves what perimeter and area mean. Right? So the perimeter of some shape is the length of the path that outlines the shape. Right, so here I can just draw some random shape here. Maybe I'll just draw it like this. So here's my shape. And so I'm just going to make up some reasonable measurements for the side lengths of this shape. Maybe I'll say that this is 4 centimeters long, and here this one looks a little bit shorter, 2 centimeters. I'll call this 8 centimeters. This is just for the sake of example. Maybe this is 6 centimeters, and this is 5 centimeters. So the perimeter of this shape is really just the idea of, we're going to sort of trace the outline of this shape and add up all of these side lengths. And this is the total length of this path. All right, so in other words, here we would take, if we kind of imagine starting at this point, we would have 4 centimeters added on with 5 centimeters, with 8 centimeters, 2 centimeters, and then lastly 6 centimeters. And so here this comes out to be, this would be 4 plus 5 is 9. On top of that, 8 gives us 17. Here we get 19, and then lastly 25. So here the perimeter in this case, this would be, what did I say? I think I said 25 centimeters, right? So it's just the length of the path that outlines our shape. And then what's the area of a shape? Now this is a little bit harder to describe, but in our above example, it's really the shape or the amount of space within a flat shape. So here, the area of this shape is the amount of space contained in this shape that I've shaded in green. And so here, area, this is the space contained in a flat shape. So some examples you can think of are maybe like the floor space in a room, or maybe in a yard, or you can think of this, if you have a piece of paper, right, that's flat. It's the amount of space that paper covers. That's the area of that piece of paper. And so, it can be challenging to compute area for many different kinds of shapes, actually. These are big problems in the past, computing areas of curved shapes. This is also a big task that is sort of tackled in calculus. But areas of rectangles are actually a very friendly shape to compute the area of. And so here, let's say we have, maybe just as a quick example, if we have some rectangle here, and let's say, this length here, this measurement of this side is 3 feet, and the measurement of this side is 1 foot. No, maybe let's do a little bit more than that. Let's do 2 feet. Right, then I can imagine sort of splitting up this rectangle into, 6 different pieces, right? 6 different 1 by 1 little foot squares, right? So here we can kind of see that this is 1 foot, 2 foot, 3 feet, and then here's 1 and 2. And this naturally cuts up our rectangle into a grid, and so we get 6 different 1 foot by 1 foot little squares. And so this is what we're counting when we're measuring the area, right? So here, the area, in this example, well, it's 2 times 3 gives us 6, oops, not 6t, 6, 6, this gives us 6 square feet that we're adding together. That's really what we're counting when we measure area. How many square units can we fit inside our shape here? And in this case of a rectangle, it's just the product of the side lengths of that rectangle. And so in general, the area of a rectangle oops, I want to say rectangular, of a rectangle, this is just equal to, the length multiplied with the width. And in this case, maybe I'll call this side length the length. Maybe I'll label it with with an L, and then here I might call this side length the width. I might label it with a W. So here we might say, if A is the area, we might say A is equal to L times W. And so this is a formula for the area of a rectangle. And then this is a formula that's very specific to rectangles. It doesn't help us compute areas of any other shapes. But sometimes we can use rectangles to find the areas of other shapes. But here, this formula is specific to rectangles. So let's use this idea to find an expression for the perimeter of this shape I have here, as well as the area of this shape. And so one thing that is mentioned is that all of the angles in this shape are right angles. And so all that means is that if I sort of take any of these sides in this picture and I extend them, my resulting little sub shape here is going to be a rectangle. Right, so if I sort of extend this side here, really all the new pieces I formed, the new shapes I formed within our original shape, these are all rectangles. That's all that means. And so I definitely encourage you to pause the video and try and figure out if you can find an expression for the perimeter. Maybe let's start with that. And if you're feeling up for it, definitely encourage you to try and find an expression for the area as well. But we'll talk about this in just a moment. So the perimeter of an object, it's really just the sum of all the side lengths. It's the length of the path that we make to outline the shape. So if I sort of imagine traversing the edges of this shape, and I add up all those measurements together, we would get the perimeter. All right, so maybe I'll kind of imagine I'm starting here and I'm walking around this shape. But one difficulty we have is that we don't have all of the side lengths, right? But something that's very convenient with rectangles, maybe I'll draw an example below, is that the sides opposite one another in a rectangle are exactly the same, right? So here, earlier we said we had an example where one side length of a rectangle was 2 feet, the other side length was 3 feet. Well, that means that the side across the 3 foot side length, that's also 3 feet long, and the side across the 2 foot side length, that's also 2 feet long. And so we can use that idea to figure out some side lengths in our original shape we have above. Right, so here, how does this idea help? Well, notice that if we kind of imagine there being a side here, there isn't, but if we sort of imagine that there was for a moment, we would be looking at a rectangle, right? And so notice that here, we're missing this side length, but it's the same as the side opposite this rectangle. This is also 6 inches long. And then, notice that here, this side is opposite this side. And so if we know the side of the side length, the measurement of the top side, we would know the measurement of the bottom side as well. Right, well here, this side consists of 3 inches, 4 inches, right? This is 4 inches because it's opposite this side length here. And then here it's 1 inch on top of that. So 3 plus 4 plus 1 together they make 8, right? So this side length here, maybe I'll say that this side length, this is 8 inches long. And this means that this side opposite, when we're looking at this big rectangular figure, is also 8 inches long. Okay, so now maybe let me do some erasing here. We don't really need all of this anymore. And we've got just about every side length. I guess there's one that we haven't figured out. There's this one here. But notice that if we kind of imagine this small rectangular figure, maybe I'll outline it in orange. This side that we're missing on the right, that's the same as the measurement of the side on the left. That's y inches. Although we don't know it, that's whatever y is, it's going to be the same value on the right side as it is on the left. And so there we have it. We have everything we need to find the perimeter of this shape here, right? So here, if I imagine starting at this point in the top left corner, and I walk around our figure, and I add up all the side lengths, well, we would get 6 plus 8 plus 6 plus 1 plus y plus 4 plus y plus 3. And so here, there's a lot going on in this expression. We can actually clean this up a bit because I know, for example, I know what 6 plus 8 is equal to. And I know what that plus 6 would be equal to, or plus 1. I can put these together, right? Order of addition doesn't matter, so I can kind of put my numbers together. And so this can actually be what's called simplified as well. 6 plus 8, that's 14. And then if we add another 6 on top of that, that'll be 20. Plus 1 gives us 21. Plus 4 gives us 25. And then plus 3, that gives us 28. So here we have 28. And then we still have this plus y and plus y. Right, so plus y plus y. And there's a way we can simplify this, but that's a topic for another video we'll get to later. But as this here is an expression for the perimeter of this shape. If we knew the value of y, or if we were given some value of that side length y, we would be able to find the perimeter by just plugging that value into the variable y here, both of these y variables here. Okay, so what about the area now? So this is a little bit more challenging, but one thing that's kind of helpful to notice, and I'll do some erasing here. So we've already taken advantage of this earlier. We said, that you can kind of picture that if we connect this side length here, that side isn't there, but if we kind of imagine that line being there, we can see, a sort of big rectangle. And a little rectangle. And so we wanted to find the area of the original shape, the space inside our original shape, so this area here, shaded in green. And so notice that that's the area of the big blue rectangle, but then take away the area of this orange rectangle, right? So this was empty space. It's not contained in our original shape. And so we want to exclude that. But so one thing we can do is we can imagine taking the area of the big rectangle and we can subtract away the area of the small rectangle. And that'll give us our area where we desire, the area shaded in green. And so what's the area of the big rectangle? Well, earlier we said that this side length was 8 inches, right? Because it came from adding on 3 on top of this distance here is 4 inches, and then plus 1 here, that totals 8 for this entire top side. And so the area of this big rectangle, well, that's 8 times 6, right? The length times the width. So here the area of the big rectangle, that's 8 times 6, that's 48. And here we're measuring area, so this is in inches squared. Well, here this was, yeah, inches squared. And then what's the area of the small rectangle? So that's this area, that's the space we're missing. It's kind of a mess now. Maybe let me erase a little bit. Well, the area of this small rectangle, will it's got a measurement, side length measurements of y inches and 4 inches. So if we multiply these together, that's going to be the area of that small rectangle. That's 4y inches squared. Right, so here, I guess I did this in orange above and I'm describing it in red down here, but this is 4y inches squared. And so we're going to subtract these two away from one another. That's going to give us the area of our original shape. And so as an expression, maybe without the units involved, this would be 48 minus 4 times y, which we would just write as 4y. This is an expression for the area of our shape. And this is not the only way you can answer this kind of problem. Here we saw this shape as one big rectangle take away a smaller rectangle, but you can also, I think it's a little bit more challenging in this example, but you can also split this up into smaller rectangles and add them together. So my pen isn't quite working right now, and that's kind of frustrating. Let me try this. Okay, so here we go. So here, if we kind of imagine slicing up this shape in this way, we see 3 different rectangles, and if we find the area of these 3 rectangles and add them together, that would be the area of the original shape. So this would be a second way you can find an expression for the area. So let's take a look at one last example. Here, this is a financial example. It says that Alex spent $3 to set up a lemonade stand, and by the end of the day, Alex sold $21 worth of lemonade. So there's some language I like to introduce. So here, Alex sold lemonade and they pulled in a total amount of $21. So here, the money that you make from selling goods or materials or services, here, this is what we call revenue. Right, so this is money made from sales. Or an income. But then here we also see that Alex had to spend some money to create this service or to sell these goods. And so here we call this amount the amount that Alex spent to set up their service. This is referred to as a cost or maybe an expense. And so here, I would like to mention that the profit that Alex made, well, here that's equal to the revenue minus the cost. And so this might seem like a very basic example, but it's one worth mentioning. Here, if we take the money that a person's made and then we subtract away the cost it took to make that money, well, everything that's left over, that's really the profit. And so here, if we used letters to represent profit, revenue, and cost, we might say that P is equal to R minus C. And so in this example here, Alex, they had a $21 revenue. There's a $3 cost, and so in this case, they had a profit of $18. And so at Hugo's Auto Shop, they paid $4,000 in expenses this month. And so if we wanted to write an expression for their profit in terms of their revenue, well, here we know that profit can be expressed as R minus C, right? Revenue minus the cost. And so here in this case, we see that there's a $4,000 expense. This was the cost for their auto shop. And so here really the expression for their profit is, if we label revenue with R, this is R minus 4,000. And so here if we look down to our example, or the little problem statement below, it says evaluate your expression that R is equal to 6,500 and explain the meaning of your result. So remember that evaluate, so what this means is that we're going to plug in this value for the variable in our expression, and we're going to compute the result. So here this is saying I'm going to take R and I'm going to replace it with 6,500. Right? And the rest of my expression says, well, R minus 4,000. And in this case, R is 6,500. And so this comes out to be 2,500. And so what's the meaning of this result? Well, this is just saying that, 4,000 was the expense, 6,500 was what they pulled in. And when we subtract those from one another, we get the profit, not month. So here, this is just saying that the profit at the auto shop was $2,500.